Hey guys, so chances are if you watch our videos, you've probably been exposed to binary, octal, hexadecimal, base 256, and these sorts of things. But a lot of people have actually asked me to explain the way that I convert from one of these base number systems to another one. And for those of you who haven't learned binary yet, pay attention to this episode because you'll learn how to do it and you realize that you already knew how to do it from the beginning. So take any normal number that you'd expect to see, like 42. Okay? Now, if you break that down, you know that it's the same as 4 times 10 plus 2, or 4 times 10 plus 2 times 1. It's 4 tens and 2 ones. And this is how we break down decimal. And decimal in this sort of context is known as base 10. So basically what we're saying here is that the 4 is in the tens place. Now, I'm sure you guys have heard of the tens place and the hundreds place and the thousands place. And a lot of people just sort of learn this or at least picked up the shortcut of just, when you're dealing with base 10, you just add a 0 for each place value. And that's one way of looking at it, but that's not really how it works. Let's break down how it actually works. Okay, so 100 is 10 times 10. Okay, so it's 2 tens multiplied together, and 1,000 is 10 times 10 times 10. 3 tens there, and 10,000 is of course 4 tens. But there's a shorthand way of doing that, which I'm sure everybody learned in school, using exponents. So 10,000 is the same as saying 10 to the power of 4, and 1,000 is the same as saying 10 to the power of 3, and 100 is the same as saying 10 to the power of 2, and 10 is the same as saying 10 to the power of 1, and here's where things get useful. 1 is the same as saying 10 to the power of 0. And this is the key that unlocks base conversion, the ones place. So let's break down 42 using exponents of 10 as our place values. It'll break down to 4 times 10 to the power of 1 plus 2 times 10 to the power of 0. Note how we start at 0. In base 10, just like all other bases, you start with 0. In base 10, we have 10 digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And to represent any number larger than 9, we need to add an extra place. And then we can get to 10. Speaking of 10, this is base 10. So if we go to our exponent sheet again, we can actually replace the 10 with a b, because we know this is our base. And here is the first step where we're actually getting to a real algorithm. And just like we know that we can replace 10 with b, we can also replace the power to the 1 and power with the 0 with to the power of p if we know that we're going to be going through a step for each place. So, algorithmatically, for each p, t equals t plus vp times b to the power of p. And that's really not as complicated as it sounds. T starts out as 0, and then you do the lowest value place, 2 times 10 to the power of 0 if you replace the VP, the B, and the P with the actual values, and we get a 2. And then we add 4 times 10 to the power of 1, which comes out to 40, for a total of 42. So basically, VP times B to the power of P is simply a symbol translator. And here we have translated from base 10 to base 10, but let's do something more interesting. Binary or base 2, and just like base 10, which has 10 digits, base 2 has 2, and we start from 0, so our digits are 0 and 1. And if we calculate our place values by doing exponents of 2, starting from 2 to the power of 0 and so on, we get 1, 2, 4, 8, 16, 32, 64, 128, and for you overachievers out there, 256, 5, 12, 10, 24, 20, 48, 40, 96, 81, 92, 16, 3, 8, 4, 3, 2, 7, 6, 8. So let's count a little bit in binary. And the first thing we need to realize is that while they're called digits in base 10, 10 digits, it's bits in binary. So when we start from 0, we're going to count up. 0 is the same in both 0 and 0. 1 is the same as both 1 and 1. And that's because we haven't had to add a place yet. But when we get to 2, binary can't represent 2 without adding a second place. So it becomes 1, 0 because we've added a 2's place and drop back down to 0 on the 1's place. And then 3 is 1 and 1. So there's a 1 in the 2's place, a 1 in the 1's place. And then with 4, we roll over again. We have to add a place, and there's a 1 in the 4's place, a 0 in the 2's place, and a 0 in the 1's place. So, like I said, you already know how to do this. So let's take a random binary number and use the algorithm that we cooked up earlier to convert it over to base 10. And just like with base 10, how we start from the least significant digit in binary, we need to start from the least significant bit. And in both those number systems, that's typically on the right-hand side. So 0 times 2 to the power of 0 is 0. 1 times 2 to the power of 1 is 2. 0 times 2 to the power of 2 is 0. 1 times 2 to the power of 3 is 8. 1 times 2 to the power of 4 is 0. 1 times 2 to the power of 5 is 32. Now we can throw those zeros out and just add up the 2, the 8, and the 32, and what's that equal? Our old friend, 42. So binary makes an excellent example for the minimalist number system because it has just the 2 symbols, and that's pretty much the lowest number of symbols that you can have and still be useful. Now, so you got base 2, you got base 10. Let's go in the opposite direction and see what happens when we have a base that has more than 10 symbols in it. One of the most popular ones is hexadecimal, or base 16. That has 16 symbols. We, of course, start from 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. Now, if we take those, what we would think normally of as letters, and convert them over to base 10, they would be 10, 11, 12, 13, 14, 15. But this is base 16, so it can represent numbers that would take more than one symbol in base 10 to represent, and it can represent them with just a single symbol, which is pretty handy. Now, if we calculate out the place values for base 16, we get 1, 16, 256, and 4096. So let's take this random number in hexadecimal 2A and run it through the same algorithm that we've been playing with. We start with the least significant symbol there, which is A, and A in base 10 is 10. So 10 times 16 to the power of 0 is 10, and 2 is in the 16's place. So 2 times 16 to the power of 1 is 32, and then we add them together. 10 plus 32 is... Too easy for you? Well, you already know how to convert between base number systems, so pretty much everything's easy from here on out. Well, maybe. There were exactly 42 slides in this presentation, and if you were to treat them as sequentially rising values of symbols in a base 42 number system, and then you took these 3 slides as your base 42 number and used the formula to convert that over to a base 256 number, and then displayed the base 256 number to yourself in ASCII text encoding, there might be a secret message. Well, thank you for watching the whole thing through, and I hope you found this thing very educational. And yeah, turn in your homework down in comments.
We post videos all the time, so don't forget to subscribe. And follow us on Twitter at TYMKRS.